This chart shows exactly what happens to a video that fails to capture attention in the first 1.5 seconds. If your viewer retention drops below 40% in that fraction of a second, the algorithm triggers a distribution kill. Your video stalls at 300 views, no matter how good the rest of it is. To remain competitive in 2026, creators have been forced to adopt professional standards once reserved for high-budget studios. Success now requires native 4K generation, flawless temporal coherence, and a level of pacing designed to withstand the shrinking attention spans of a modern audience. But look at the alternative. If you hold viewers past that initial drop and maintain a completion rate above 70%, you hit the exact mathematical threshold required to trigger viral distribution. Hitting that number requires precise psychological triggers and intentional pacing. Viral success is a highly engineered outcome. We are going to take a notoriously dry academic subject, the history of ancient cartography, and build it into a high-retention cinematic piece to prove exactly how this pipeline works. Executing this requires 3 distinct pillars: search-first ideation to find the audience, physics-based AI generation to build the visuals, and professional-grade post-production to tie it all together. We start by looking at search data. Before we even think about turning on a camera or opening an editing timeline, we have to isolate a specific algorithmic demand that our target audience is actively searching for. In today's attention economy, presenting complex historical facts isn't enough to hold a viewer. We have to wrap that academic information in blockbuster production values just to keep them from scrolling away. In the past, creators would stuff their descriptions with isolated keywords, hoping to catch a stray search query. Today, Google's Search Generative Experience, or SGE, requires what we call topic-first clustering. This illustrates a semantic web. Instead of chasing single phrases, we build interconnected content around a central theme, proving topical authority to AI parsers. We reinforce this with specific title structures, XML sitemaps, and accurate transcripts, ensuring the algorithm understands our exact topic. All of that structural data dictates what we show in the first 1.5 seconds of the video. The opening frame has to prioritize immediate psychological tension to hook the viewer. Before a single frame is generated, the video has a dual purpose. It must be instantly compelling to a human mind and structurally legible to an AI machine. Once the framework is set, we move into production. For historical sequences like our geography case study, we rely entirely on the latest image-to-video generation models. The major leap this year is the introduction of the AI physics engine. Older models would simply warp 2-dimensional pixels to fake movement. Now, the AI simulates real-world gravity, mass, and depth. You can see that physics engine at work here. When the heavy brass astrolabe violently hits the dark water, the model calculates photorealistic buoyancy and liquid displacement, making the environment behave exactly as it would in real life. To maintain immersion, we use an identity lock feature. This forces the model to keep our historical figures wearing the exact same clothes and maintaining identical facial structures across entirely different camera angles. But entirely digital scenes can still feel artificial, so we intercut these generated shots with traditional B-roll, specifically using a 50mm f1.8 lens mounted on a gimbal to add authentic kinetic motion and a shallow, organic depth of field. By synthesizing mathematically perfect AI physics with the natural optical imperfections of a real camera lens, we blur the lines of reality. The viewer, and the algorithm, accept the footage as real. The final phase happens in post-production. We use a node-based workflow to process those raw pixels and give them a cinematic aesthetic. The technical foundation of this grade relies on DaVinci YRGB color management. It automatically maps flat, low-contrast camera profiles into a standardized viewing space. This waveform scope shows our primary correction. We stretch the signal to establish a dramatic contrast ratio without clipping highlights or crushing shadows. Then we degrade the sterile AI media, introducing analog film grain and a subtle red halation around the brightest edges. Finally, we build the soundscape. Layering atmospheric orchestral tension directly underneath the voiceover dictates the emotional pacing and actively prevents viewer drop-off during quieter moments. These final adjustments turn a series of raw technical signals into a specific, cohesive mood that helps the entire narrative feel intentional to the viewer. This is the finalized sequence. It brings the history of geography to life through a seamless intersection of search data, AI physics, and cinematography. This video is a highly structured digital asset, engineered from the start for maximum platform visibility. Every frame and metadata tag has been calibrated to trigger specific discovery mechanisms within the ecosystem. Because we integrated precise schema markup, XML video sitemaps, and complete transcripts, AI answer engines can easily parse the footage and cite it across the internet. Dominating YouTube in 2026 isn't about hacking an algorithm. You have to architect an undeniable digital reality, one that perfectly satisfies the emotional needs of the viewer and the structural logic of machines.